So today I will be demoing my tool called DarkWidow, which is a customizable dropper toolkit targeting Windows. So little bit of a background about me. I work as a associate security consultant at Payatu. Most of my daily work includes research and development on malwares and evasions and red team on on-prem and cloud environments. I also have a little bit of a Linux internals background and currently doing most of the research in Windows internals. Yeah, been an international speaker, as he already told you. And like last of all, that I want to thank Farhan Siddiqui, who was actually my ex-coworker, for helping me to build these slides. So the agenda for today is the basics, the Windows internals, that user land versus kernel land. Then I would be showcasing how EDR perform hooks and some of the bypassing strategies of that. Then I will be introducing system calls and then direct system calls, then indirect system calls. Then comes the introduction of my tool called DarkWidow. First, I will be showcasing version 1 and then I will be demoing my version 1 of my tool. Then a new concept comes, that is synthetic frame thread stack spoofing. And then I will be showcasing the version 2 of my tool and then the future updates. So the basics. So when a particular process um, calls a particular API, in this case Win API, and here the Win API is create file A, and it's get originated from a DLL called the kernel32.dll, and it goes through another DLL which is ntdll.dll, and this Win API gets converted to its nt API form, that is nt create file, and then after that it gets converted to syscall. And when it gets converted to syscall, it directly enters the kernel and do its certain action. In this case, if this whole procedure uh, performed successfully, then a file is created successfully in the Windows operating system. So now, if EDRs are basically present in that particular environment, what it would do? Let's say a malware process is running and it actually calls a Win API called virtualloc.ex, which is present in kernel 32, and then it goes to ntdll format of it, that is nt allocate virtual memory. And then if EDR is present, as I already mentioned, EDR places a hook into this particular nt API. So in the assembly language, if we explain a hook, it is basically a jump instruction. So now what happens is the control gets jumped from this nt API to EDR DLL. And now the EDR.dll checks whether this API is malicious or not. If it is found to be malicious, it terminates the process. And else, like if it doesn't find it malicious, the control goes back to this nt API. Then again, it calls system call and it does a certain task. So this is how EDR hooks. And if you see this picture, this is how int API looks when it is present under a debugger. And this like bunch of codes or bunch of assembly languages actually showcases system call stub of a particular int API. And you can see this particular number 18. This is the system call number. And in this case, the system call number is belongs to this ZW allocate virtual memory. And in this case, EDRs haven't placed it hook. But in the second picture, as you can see here, there is a jump instruction. That means EDR has placed a hook in this particular API. And the address which is present here actually corresponds to the address of the EDR DLL, which is being placed into the process. So there are some notable EDR bypass strategies, that is NT API hooking, repatching, manual mapping, and overload mapping, stuff like that. But these are not my like agenda for today. But these two would be the agenda for today because these two would be present in my tool. So first one is syscall usage to bypass API hooking, which would be present in the version 1 capability of my tool. And the next comes is thread stack spoofing, which would be present in the version 2 and which would help us to evade call stack based detection, also called stack monitoring, which is done by ETWTI. So as I already mentioned before, let's go it again, that let's say malware is running in the user mode, that is ring 3, it calls a Win API called virtual-alloc-ex, goes through kernel 32 DLL, then goes via kernel-based DLL, then goes to NTDLL, and it gets converted to NT-allocate virtual memory. Then if EDR is present, EDR would hook that NTDLL, and the control will jump into the hooking.dll, and again all those stuff. So one thing which you can see here, that EDR places hooks in the NT API, that is NTDLL. So to get around that, what we would do is we can directly enter the kernel. You can see here we are not involving these DLLs at all. So via that method, we would be able to evade the NTDLL hooking. So in here, you can see this is the malware process. And what we have done is we have directly pasted the system call stub within the process. So now the system call would be executed from within the process and would directly enter the kernel. And via this way, we would be able to evade NTDL hooking. So the ways of doing that, there are two ways. The first one is static hard-coded syscalls, and the second one is the dynamic hard-coded dynamic syscalls. So the first one actually shows you that the syscalls are hard-coded in here, and the second one it shows you that you can see all these system call stubs, right? So what it would do is you can see there is BA, BB, BC, and BD. So the system call numbers are actually incremented by 1. So this is basically the algorithm which we would be able to dynamically sort SSNs. So there are some of the extraction methods for direct system call. The first one is the well-known Hell's Gate. But the thing is, it falls short when NT APIs are hooked, because it doesn't actually have any mechanism to detect whether how to actually detect NT APIs or hooking of NT APIs. So for that reason, a modified form of Hell's Gate came into picture, that is called Hallow's Gate. So let's say you can see this picture. We want to call a particular Win API called ZW allocate virtual memory, and we know that that particular API is hooked. What we would do is we would check its neighboring API. So in this case, the neighboring API system call is 17 and 19. So what we would be doing is we would be adding 1 to this, becomes 17 plus 8, 1, 18, and subtracting 1 to 19, that becomes 18. That means the system call number of ZW allocate virtual memory NT API becomes 18. So now we would be having the system call number of this hooked NT API. So via that, we would be actually executing that NT API, and that's how we would be able to evade NTDLL hooking. So another modified form of Hallow's Gate comes. So basically the concept is same, but you can see here that a jump instruction is present in the first position. But what some EDR do is they places their jump instruction in third position. So to evade that, the TartarusGate came into picture. The first position, it checks for the first position as well as third position for the jump instruction to check the hooking. And modified TartarusGate is also the same. It basically checks all the possible positions where EDR can place its hooks. And this modified TartarusGate approach is present in my tool. So there are some drawbacks of the direct dynamic system call, or I would say direct system call rather. So if you see, if we use obj dump against a particular exe or binary which performs static direct system call, it would be able to dump all the system call stubs which is present within the process, as I already mentioned before. And this is kind of an IOC which we don't want. And another thing, if we perform dynamic direct system call, then there is a technique called instrumentation callback, or aka Nirvana, which would be able to detect that. Because normally the flow is like notepad process is created, then it would go via kernel 32, then it would go via kernel base, then NTDLL, then kernel boot. But in this case, for direct system call, it is directly entering the kernel. So that is kind of an IOC. So you can see here in the screenshot that I executed Hell's Gate, and Hell's Gate was able to retrieve system call number. And as soon as it was able to retrieve the system call number and entering the kernel, this particular POC, which has the capability to detect manual, like direct system calls, actually detected this and produced an alert and terminated the process. So this is basically the drawback of the direct system call. So this is how it is basically detecting that. So whenever it is actually entering the kernel, it is checking the return address. So here the return address is not NTDLL. It is the return address is coming from the malware.exe. So to get around that, what we would be doing is we would be extracting the SSN, then jumping into NTDLL, and then trying to enter the kernel. So now if the EDR checks the return address, it would be able to see that we are actually returning from NTDLL, not from any other module. So now we would be able to evade instrumentation callback. And this particular concept is called indirect system call. So now let me introduce my tool. So the capabilities which my tool possesses are indirect dynamic system call, sorting of SSN and Syscall addresses via modified TartarusGate approach, remote process injection via APC early bird to cut off EDR telemetry caching, then spawns a sacrificial process at the target process, which doesn't interrupt any already open process in the environment. Then ACG and BlockDll mitigation policies are present on the spawn process. Then PPID spoofing, then API and DLL resolving from TIB is done, and then cars NT API hashing is also present. So capability 1, these two snippets actually help us to retrieve SSN as well as system call address via updated TartarusGate approach. And those two snippets, this one and this one, is basically two functions. You can see here, this is the sort SSN and sort syscall address, syscall instruction. So with this, we are able to get the SSN number and SSN address. And after retrieving those, what we are doing is we are passing those values to this assembly procedure. And this assembly procedure is basically storing those values within these two variables, SSN and syscall address. After storing that, it is executing this assembly procedure is being executed, and then the indirect dynamic system call is actually performed. So yeah. So if you see the thread stack, this is a legitimate CMD process, and this is our implant process. So you can see here the 6th frame and the 5th frame. The 5th frame shows intos kernel.exe. That means it is entering the kernel. It is entering the kernel from ntdll.dll. This is our malware process. And in the legitimate CMD process, if you see here the 8th frame, intos kernel, and it is returning from ntdll.dll. So in both cases, it is returning for ntdll.dll, the implant process as well as legitimate CMD process. So our malware looks somewhat of a legitimate thing. So then comes the remote process injection via APC early bird. So recently I saw a post by Elastic. They actually mentioned that using Q user APC call stack not always available due to ETW limitation. So I thought that I can actually target this and take advantage of this. And what I did was took the NT API form of Q user APC, that is NT Q user APC, and used that to perform process injection. So in that way, we would be able to evade some of the EDRs. And I used create process a win API to perform like spawn a sacrificial process at the target process. In this particular example, I use security health history to be spawned. You can actually customize to any other process like runtime broker and things like that. So now comes the capability 5. So here what I introduced was ACG and BlockDll mitigation. So these two things would be helping us to block EDR DLLs to be placing its hook within our malware process. But this thing have a drawback that if the DLL which is being injected by the EDR is actually signed by a Microsoft certificate, then this BlockDll won't work. But in that case, indirect system call is there, so we won't have to worry. And again, it comes PPID spoofing portion. So now if you can see here in this demo, like in this screenshot, that it is spawning a process called 23036 PID, and its parent is being changed from cmd.exe to, as you can see, it is like spawned from a cmd to explorer.exe. It becomes 8464, and acg and cig is also enabled successfully. Then comes capability 7. So to resolve the DLL as well as the API, normally what we do is we actually access PEB, and for that we have to access GS060. But I actually avoided that to evade some of the EDRs. So rather than directly accessing the PEB, what I did was I indirectly accessed PEB via TEB via GS030, and this actually helped in evading some EDRs as we are not directly accessing PEB. Then after getting the address of the PEB, I targeted another special structure called loader module list, because this special structure contains all loaded modules which are present in order when processes basically got loaded. So from there, I was able to retrieve the address of the NTDLL. Then after getting the address of the NTDLL, I was able to get the address of the NT-APIs. So this is the snippet via which I was able to retrieve the address of the NTDLL dynamically. And this particular website called react.org, reactos.org, actually helped me to get the snippet. Yeah. So after getting the address of the NTDLL, I was able to retrieve the address of the NT-API. So here in this line, we are actually extracting NT-API function name. After extracting the NT-API function name, I am passing that function name to this particular function DJB2. And DJB2, if you all know that it is basically a hashing algorithm. So what it does is it creates a hash of this function name and checks with the hard-coded hash, this is the hard-coded hash which I have mentioned here. So if these two hashes matches, then this process becomes successful and it goes on performing NT-API execution via indirect system call. So this is the DJB2 hashing function which I used for performing API hashing. And these are two functions, resolve DLL. So this function actually helps us to resolve NTDLL or any DLL if you want, and just you have to give a hash in this particular area. And the resolve NT-API actually help us to resolve like any API you want from any DLL. So yeah, these are the two functions to resolve DLL and NT-API. So one extra capability is there. If for some reason we got admin privilege and our malware is running on admin privilege, it would be able to kill the responsible SBC host, which are actually responsible for logging. So you can see here, from here, it is on elevated stage, but AC debug privilege is disabled. So now what it would do is, it would turn on AC debug privilege and it would target or hunt down that particular process which is actually responsible for event logging. Then after hunting that down, it would target all the threads which are particularly responsible. Then it would kill those threads and it would perform shellcode execution. Let's show you the first demo. So now our malware is running as a non-admin privilege and Sophos XDR is running in the background. It is not a notepad, it is basically malware. I just changed the name. And here the MSF console is running. It spawned the process. Everything worked successfully. No notification came up, nothing. And we can see we got a shell. Let's see. Again, nothing, no notification till now. Just checking the IP address 102. Here also 102. Let's see. And see, no notifications, no alerts. We were able to bypass Sophos XDR. So let's see how it performed again event logging. No critical alerts was there except one, which was a low CBIT alert, that is asynchronous procedure call. I will be showing you how to evade that as well. But before that, let me show you how my implant performed when it had admin privilege. Again, the same thing, but we have admin privilege. Let me fast forward a bit. So it tried to kill all the event logging threads which are present, but it was unable to, because event logging, in this case, event logging threads were not present. So it like proceeds down to its post-exploitation phase. So let me show you. Yeah, you can see we got a shell and no alert actually pop up. Just a minute. Yeah. Yep. No notification. So let's see now what are the event logs that were generated. Again, the APC injection was present. That's why asynchronous procedure call log was there. And another new log came into picture, that is user account was changed. So I kind of dig into that and found out as I used AC debug privilege, then that's the reason why this particular logs got generated. But this log is under medium alert. So this is kind of a concerning thing. So to get around that issue, I introduced a concept called synthetic frame thread stack spoofing. So now let's get into this picture, that what this synthetic frame thread stack spoofing does. It basically enables us to bypass call stacks monitoring. So you can see these two pictures. These are thread stack frames of two malwares. You can see the first picture, that the 10th frame and the 11th frame. So here it is calling get host by name, and it is coming from, it is called via this particular address. And this particular address is basically a leak stack value. As it, you can see that it is not being called by any DLL or API. And mostly this leak stack value has a permission of Rx memory region, that is read executable. And mostly it is unbacked by any module. And that's kind of a concerning thing, because if EDR utilizes ETW tracing and checks this whole thread, it would be able to detect our malware. And we don't really want that. So to avoid that issue, we have to do two things. One, to hide our source, hide our malicious NT API function call via stack spoofing. That is number one. And the second one is, if you see this cmd.exe, which is a legitimate cmd.exe, so the thread stack frame always and always starts with two frames. That is, first one is RTL user thread start, and the second one is base thread init thunk. So what we would be doing is, before, you can see here the last two frames were arbitrary leak stack value. So we would be creating two fake frames which would be looking like a legitimate frames like this one, and we would be sticking that on the top of the stack. And after that, it would look kind of like this. You can see here, this is the NTAPI thread stack, and you can see it is pretty much a legitimate looking thread stack. And the shellcode thread stack look kind of like this. You can see here, RTL user thread start and base thread init thunk. And in this case, the shellcode which I used is created by Havoc, which is an open source tool. And this is basically the configuration which I actually used. So one thing to be noted, that if you want to evade as many EDRs as possible, please try to change the algorithm of the stack spoofing. Please try to see what are the ways the EDRs are detecting and stuff. So yeah, because it is a cat and mouse game. And also you can change the shellcode execution APIs to fibers, TP allocate, TP set weight, create thread pool weight, set thread pool weight, etc. And it can also be weaponized to perform DLL side loading as well. In this picture, you can see here, I was able to evade Cortex. So what I did was, I performed a DLL side loading, and I like transformed that particular POC, the DarkWidow one, into DLL, and removed the remote process injection into local process injection, and used brute rattles shellcode, and I was able to evade Cortex. So yeah. So let's see the version 2 of my demo. So in here, yeah, again, Sophos XDR is running. Then notepad is, it is not notepad, it is my malware. I just name that like that, name the binary like that. You can see runtime broker is spawned with PID 12628. Yep, it is spawned. Then the process injection got successful. And you can see no new notifications. And I got a shell in Havoc. I will be pasting all the commands in a notepad. I will be showing because this is kind of a small. I did who am I? You can see here. And I would be performing a service enumeration to show you what are the services that are running in the background, to showcase that Sophos is running. Then also it was not able to detect our malware. Yep. You can see here Sophos file scanner is running in the background, and Sophos live query service is also running in the background, but then also it wasn't able to detect our implant. You can see again no notification came up. Now let's see how it does against event logging. Now you can see here with this approach, no log was actually generated and we were able to evade successfully, like completely. So yeah. So there are some future updates to my tool, like porting this version to C++ clamp compiling for performing LLVM obfuscation, manual load library capability to bypass image load kernel callbacks, applying module stomping capability, or encrypting the shellcode injection to avoid kernel triggered memory scans, which is also called Karokan. So in this Thanksgiving portion, I want to thank Peter Wintersmith, Bobby Cook, Alexandro Magnosio, Shomadip Basu, John Meese, Jan F. Renzo, Daniel Fischer, Dylan Tran, Jackie Callan, Sadala, Upansha, Ponulgun, Ungur, and Monappa, because all of these guys actually helped me to build this tool. So yeah, that's kind of from my side. So any questions?
Did you test against any other ERs like Windows Defender?
I guess just against CrowdStrike.
Okay.
Yeah, it worked. In that case, you have to change into local process injection, and you have to change the shellcode execution to fiber. Yep, in that it would work.